Hello one and all, and welcome to the Math Magic Show. In this one we're going to study waves using the simulation from phet.colorado.edu. So it's called the Waves Intro. They have a great collection of things like this online, not just for waves but for a lot of other topics in the sciences and so on. I love it. So let's take a look here. I have basically a faucet. I'm going to press this button and let's see what happens first. Okay, when you press the button you see drops. And then whenever the drop hits, you see little circular waves spread out from where the drop hits the water. Over here, on this side, there are two things. It says frequency and it also says amplitude. Let's vary these. These are sometimes called parameters in the sciences. So these are things that use value you can change, for example. And we'll see what happens in terms of the waves that we see spreading out from where the drops hit. Okay, so I'm going to change the frequency. Let's see what I mean by changing the frequency. So we build some physical intuition for the meaning of frequency in this simple situation. Take a look. I'm going to make it as big as possible. I'm maxing out the frequency. And look, you see the result is that now the drops are falling more quickly. But if you look at the waves, the blue areas, the circular areas, as you can see, appear to be a bit smaller than before. Take a look. If you decrease the frequency, if I pause this for a second, take a look. Let me take my measuring tool here, and if I measure it over here, you see right now the frequency is at a max. So when I measure this, it's about 1 centimeter across this way. See the blue area that is. So let's see what happens when I make the frequency as small as possible. Keep that in mind. So I'm going to make this as small as possible. Hit play. Give it a little bit of time, and then we'll freeze it at some point in time. Okay, so take a look. You clearly see there's a giant difference, right? When the frequency is smaller, then the waves are much wider. So in other words, take a look. Just this portion of it alone. You see, that's like maybe 4.5 times as wide as before. So that's one thing to be observed. That's the meaning of the frequency. Now, let's also take a look at the amplitude. But to do that, over here, take a look. Under this thing it says graph. So I'm going to enable the graph. Okay, so that enables a new graph feature down on the bottom. I really like this one. Let's study this up a little bit. So what is this graph measuring for us? Here, as you can see, it says water level. And then here, on the bottom, across the bottom, that is, as you can see, it says position. So what this is doing is telling you the water level at a given position, okay? Now, this graph is kind of frozen in time for a second, but we can still tell the following, that, like, for example, you see this water level is high here. And notice there's no drop coming out of the little pipe. Now think about how real water behaves, right? When the drop strikes the water, it makes the water go down a little bit. And then when no drop is striking the water begins to level back out, correct? Sometimes up a little bit. So that's why this graph right here is peaked. Now, I'm going to reset the frequency to a higher value so we can see how this graph connects to the picture above. Okay, so I'm going to set the frequency, say, at this value right here in the middle, between the min and the max on the right side. And let's play this. Take a look. Okay, play. Let this stabilize a little bit. You want to develop a nice wave pattern radiating from where the drop strikes. And here, there are some key characteristics that we want to observe. Okay, so I'm going to stop this for a second. That's pretty good. Okay, now what makes a wave cycle? That's what we have to define. So when you look at this graph, you see usually we measure, for example, from like peak to peak or trough to trough. That's what makes a full cycle. So in this particular case, let me see. I'm going to do the best I can. It's probably not the best thing to use this part right here because the water is kind of crazy going up and down, oscillating. But using the stabilized wave maybe over here, at this distance, you see, you might measure the cycle this way, look. This would be a cycle. So it's about 2.7 centimeters. That is a wave length. And we define that as such because, as you can see over here, you see this is a peak, a trough, and a peak. That defines a cycle. If you look at the picture above that corresponds to it, it gives us a clearer picture of what we mean by a wavelength. So take a look. If you go up here, you see it goes from this peak. So this portion right here, where the tape is placed, that's like the peak. That's where the water level is the highest. And then the black area, that represents the lowest water level. And then again, as you can see, it goes back to another blue area, which represents another peak. So these are just like waves rolling away from where the drop strikes. And a wave is a cyclical feature that has something called a wavelength, just the way you see it. So that's one feature. With this graph showing, it might be kind of interesting to see what happens when we change the frequency. So I'm going to max out the frequency. Right now, for example, it looks like the wavelength is about 2.7 centimeters. So let's max out the frequency, run this baby again. Okay, come on. There you go. I keep forgetting to hit play on the bottom. Now, let this stabilize a little bit. And now this is definitely a little bit different, right? Okay, let me freeze it once the waves are nicely stabilized. I guess pretty good. And this is different because, as you can see, this frequency is the maximum that this simulation allows. And when I look here, take a look. So from here to here, okay, let me see. I mean, there we are. That's about here, peak to peak. So peak to peak now, this is only about 1.7 centimeters. So what it's saying is, as you increase the frequency, you see that, for example, the wavelength begins to shrink. Okay, so the two could be said to be inversely related. So as the frequency increases, the wavelength decreases. That's what this is showing us in a simple physical way. Another thing that we can change is the amplitude. So across the top, you see it says amplitude. There's a 0 value and then there's a max value. Let's take a look at the max value. And then we'll compare it by getting close to 0. So first, let's see what happens when I set the amplitude to max. And I hit the simulation, run it again. Okay. So as you can see, at maximum amplitude, it looks like this. Here, this portion, right, seems to rise and fall pretty high, right where the drop strikes. Do you see that? It's going up and down, as you can see there, pretty high and then pretty low. So that seems to be the amplitude. It seems to really affect this area. But let's now get this close to 0 and let's run it again. We want to see what happens. That's the best way to do things. You just basically change the values and then study the system. And notice that in this particular case, the amplitude is pretty small, and that physically corresponds, as you can see, to very small water drops. You see that? The amplitude in this context, it is true. If you look along the graph, you see the black line seems to be wiggling along the graph, but it's barely rising above or below. So the amplitude is very small. The water rises or falls below the equilibrium position very, very little bit. That corresponds to a small drop. And again, if you do this on max amplitude, that corresponds to these chunky drops. Chubby Rain is a movie called Chubby Rain, I think. And as you can see, that makes the water level oscillate much more. So the water level rises above the equilibrium position more, and it falls below the equilibrium position more than when the amplitude is small. And one last thing that we can do in the simulation that I really love to help us build our intuition for waves, this is just intuition, right? If I click on the side view down below, it turns the tank, and then perhaps this is like looking at it with a glass of a fish tank, I suppose. Somebody's generating waves in it. You would see them roll away just the way we do here. So this is in the case of the big raindrops, and now, or drops of water, let's set the amplitude to basically nothing. You see little drops, and you see that the surface of the water is barely disturbed. So small amplitude, very little deviation from the equilibrium, which is here represented by this dashed line going this way. Let's also now make the amplitude big and make the frequency small, okay? So in this particular case, as you can see, it will oscillate high and low quite drastically, but because the frequency is small, the waves are very long. Do you see how long the waves are? They're very long from peak to peak. Okay, they might be even hard to measure here actually. But roughly, like for example, if I take it from here to here and here to here, that's 4.9, say 5 centimeters. That's the wave length. When you measure those things like wavelength, you want to measure, for example, from trough to trough or peak to peak. Here it would be hard to use peak to peak, right? Because this peak is like at an angle relative to this peak. You see that? And the water here around the pipe is very unstable and oscillating crazily anyway. So these are some of the interesting features that you can study about waves. For example, something like water. The amplitude of the waves, the frequency of the waves, and then understanding how big amplitude, big drops, for example, small amplitude, little baby drops, okay? High frequency, a lot of drops, right? Low frequency, not too many drops. That is it for me. Thank you so much for watching. Please leave a like and subscribe, and I will see you in another of these videos.